again, try to do this one-handed with the baby. So this is going to be, we'll call it 6.3, or 6.1. Slope fields, and differential equations. This is just, we're just going to scratch the surface of this equations. But there's an entire class of calculus at higher level math classes in college about differential equations and how to solve them, how to do the integrals of them, things like that. We will get into that. We will not get into that this class. We're just going to give you the basics of differential equations, and it's basically what we've done already with integrals. So let's first though, I want to talk about slope fields and what a slope field is and what a differential equation is and how they are connected. So a slope field is the graph of a differential equation. It represents the answer of the slopes represents the answer of the slopes at different points. So for example, a differential equation is dy dx is equal to something like x plus y. This is a differential equation. A differential equation is an equation that has this dy dx. It is an equation describing a derivative. This is a derivative, right? Dy dx is an equation represented by, well, here's a formula, here's an equation, right? It says that the derivative of an equation, the slope of that derivative, right, is equal to whatever the x value is of the equation plus whatever the y value is of the point that you're located at. So this is a differential equation. It's a derivative. It's describing a derivative, which is a bunch of slopes. So this is a bunch of slopes here, right? A bunch of slopes, and they say all of these slopes, we can calculate these slopes by looking at the location we are on the graph. Where are we on the graph? Look at the x value, the y value. This one adds them together, and that tells us the slope. Sometimes, instead of dy dx, we sometimes write y prime. These are the same thing. Y prime, right? Y prime is another way to write dy dx. So y prime dy dx, that's the slope. That's a differential equation. What we can do is, let's take a graph. We're going to write this real simple graph here. We're going to do 1, 2, -1, -2, 1, 2, and 1, -1, -2. 1, 2, 1, 2, -1, -2, and -1, -2 here, right? So I'm going to draw a little, pretty big. You want it pretty big. And this is going to be a slope field. And what we're going to do is, I'm going to draw little dots on every sort of point here. I'm going to draw little dots. So this location of this point here, this dot here, this is 1 on the x and 1 on the y. So it's the location of point 1, 1. This is 1, 2, 2, 1, 2, 2, right? And then I'm going to do the same on this side over here. I'm going to put these values here, We want a few of these. Let's just do all 8, 9, 10, 11, 12 of these here. 16 actually, 16 points, isn't it? So what we're going to do to draw the slope field, plug in the x, y point and find dy dx. Okay? And then draw the slope at that point. So for example, let's do the point 1, 1, 1, 1, right? So if I plug it, let me go over here. Draw the slope. To draw the slope field, plug in the xy point into the differential equation. You're plugging it into this equation, and you're plugging in the x and the y, and you're going to get a slope. Get an answer for what the derivative is at that location in the graph. So let's do this over here. Let's plug in the point 1, 1. So dy dx is going to equal 1 plus 1, right? This is x and y. So that's going to be 2. So at the coordinate 1, 1, right here, at this point 1, 1, our slope of the graph is 2. So I'm going to kind of draw, a line like that. M equals 2 at that location. Dy dx equals 2 at this location right here. So I'm going to draw the line showing my graph at that location, right? I'm going to do it also for point, let's do 0, 1. Dy dx at 0, 1. This is again x and y. 0 for x, 1 for y. Right, I'm just using this formula. This formula just says plug in the x value plus the y value, add the two together. X plus y. So if x is 0, y is 1, that's this location right here, right? These other points here, these other points. 0, 1, that's equal to 1. So at this point, the slope is 1. And so you see my slope here is a little bit less of an angle than the slope of here is 2, right? The slope of here is 1. Here's 2, here's 1. And you can do this for every point, right? If I do it for 0, 0, dy dx is obviously going to be 0. So that's going to be, at this point, it's going to be a flat line like that. At, let's do here, 1, 0, that's going to be dy dx is going to equal 1. So that's going to be, again, the slope of 1 like this. And if I do negatives, what about the point -1, 0? That's going to be dy dx of -1. So that's going to go right here, down 1 like that. Two there. So you see what I'm doing? I'm just plugging in the values at 2, 0, 2, 0. I'm just picking kind of randomly, but you can do this kind of ordered if you want, but you just got to do all these points, and you're just finding slope equation. 2, 0, that's going to be dy dx equals 2, so it's going to be, again, up like this. At maybe -1, 1, this point here, -1, 1, that's going to be dy dx is going to be 0 again, because we have a -1 on the x, positive 1 on the y, we add them together, that's going to be 0. In fact, it's going to be 0 for -2, 2, and 1, -1, and 2, -2. All those are going to be 0. At 0, 2, the slope is going to be 2. Here's going to be -1. Oopsies. -1. And then -2. Here's going to be -1 also, because +1 minus 2, right? So you can fill in all of these points here. At -1, 2, it's going to be a +1. Here it'll be a +1 as well. Here it's going to be +3. Here m is going to be 3. Here m is going to be 4. So you see I'm like sharpening my curve. Here it's going to be 3 again. It's like this, a little bit sharper. M is 3. Here it's going to be a -1 down this way. Here it'll be -2. Here it'll be -3. Here it'll be -4. -3, -2, -1, right? So you see these different slopes here. So you don't have to really draw a very precise graph. Here's also -2. As long as you get the idea down. This is -3 here. And this is our slope field. So if you want to draw all these little lines, I'm going to show you what this kind of looks like. Yeah, I'm going to leave those. There you go. So if we step back and take a look at this graph as like a whole picture now, right? We've put all the slope fields in here. We put all the lines, the points in here that describe the shape of this differential equation. And this is what a slope field is, right? Describing a shape of a graph. So a slope field, what it ultimately does. He's being very wiggly. Still asleep though. Still asleep. Stay asleep, baby. What a slope field ultimately does is it shows the direction of the graph at any point. What a slope field does is it shows where a graph would be kind of pushed at that particular location. And you know that these individual points are just the values we chose. I can zoom in to the slope field. I can say, well, what about the slope at 1/2, -1/2? What is that slope? Or what about 1/2, 2? What is that slope going to be? Right? I can zoom in and really there's an infinite number of slopes between this 0 and this 1, right? I can go to 0.1, 0.2, 0.3, 0.4, 0.5, halfway, right? All these different oh goodness. Oh goodness. Hold on, everyone. Hold on. There you go. There you go. How about a pacifier? Yeah. Hold on, everybody. Thank you. He was good for a while. Oh, now he woke up. Awoke, baby. Hold on, everyone. There you go, Ro. Here, have this. All right. Well, we went as long as we could. Anyway, what was I talking about? All right, slope field. So the point is, what you're seeing here in the slope field is this graph here. It shows you how you can imagine a graph being pushed along these spots, right? If you imagine like a bug or something trying to travel here, and these little lines are like the wind, pushing the graph in certain directions as it goes, right? If we started our bug here, it would go horizontal and then get pushed up, right? And get pushed up. Or if we started here, it would get pushed down this way. we started on the line here, get pushed straight along this y equals 1 line, right? Or if we moved a little bit here, we'd go flat, and then we'd go pushed up like this, right? So our graph is going to move around, influenced by all of these lines, all of these locations, pushing the graph in certain directions. And so we can imagine what a graph might look like. We can imagine what a graph might look like. If, let's do this. In this slope field, in this slope field, what does the graph look like? What would the graph look like? What would the graph look like? If it passed through the point 0, 0. Angel, Bianca, welcome. You're going to have to play this recording back to pick up the other stuff, but glad you're here. We're talking about slope fields. We created this slope field together. This is a slope field here. We drew this together by plugging in a bunch of points, all the locations of x's and y's, into this differential equation. This is basically a slope equation describing the slope, right? So I plugged in 1, 1 and got a slope of 1 plus 1, 1 the x, 1 the y, got a slope of 2. And so we created this shape here. And what we're asking now, the question now, this slope field describes where the graph is being pushed as it moves along. So the question is, what would this graph look like if it passed through the point 0, 0? Let's imagine if we were, if we were a bug or a piece of a leaf or something, and this is all the wind pushing us around. What pathway would we take through this slope field? How would we be pushed? If we started our position, if we know that our location of this leaf or bug or whatever passed through 0, 0, what would the graph look like? Let's draw this in green. F of x, basically, so we know that f of 0 equals 0, right? So f of x is a graph. Is a function, is a graph. And if we imagine going through 0, so let's just try to draw this. I'm going to zoom in here. I'm going to start at 0, 0, and I see that my graph goes pushed forward, right? So I'm going to push forward, so I'm going to go forward from here. But then immediately, I'm going to be pushed upward, right? So my graph is going to be here, and then I'm going to kind of go forward. I know my slope is going to go like this. I go forward, and then I'm going to get pushed. And I'm constantly going to get pushed higher and higher, right? You see all my slope. As I go this way, my slopes are increasing. So I'm going to be constantly pushed. Eventually, my slope will be 4, and it goes up like this. So my slope of this graph will look something like this, traveling through here like this. If I go backwards, I know my slope is going to go downward, right? So my slope must be down, and then it's got to be flat, and then down and flat, right? So something like this, maybe. And it gets flattened out as we get to 0, 0, but then it goes back up as we kind of curve around. So something kind of like this, right? Where a slope kind of gets pushed forward and down, forward and down. Maybe it's maybe it's actually going pretty straight like this. Maybe it's going to go straight somewhere like that. But this is the idea, right? You're going to be pushed around, pass through this point, go forward, and then go kind of up and get pushed vertical. As these slopes, as this wind, you can imagine, pushes you up, right? So that might be a graph if you pass through 0, 0. What if you pass through the point this one here? Well, if we pass through -1, -1, our graph is going to look completely different. Our graph would look down like this and go down that way. If we pass through the point negative 1, negative 1. Pass through the point negative 1, negative 1. Pass through the point negative 1, negative 1, negative 1. If we pass through this point, our graph is going to look much, much different. It would be downward, right? Here, this is going through f of negative 1 equals negative 1. Here, f of 0 equals 0. So we have different like starting positions. And these different starting positions can create these different graphs and different motions depending on how the initial conditions of our function were. And this is where we get into derivatives, integrals, right? When we integrate something, we have this plus c, this unknown constant that gets thrown in there. And these graphs are the These graphs are the representation of those different starting c values. What are my initial conditions? How does the graph begin? Where's the position of the graph when it starts? How does it get pushed around? So that's what these slope fields describe. It shows the direction of the graph as it travels through this sort of waves of pushing. And these are equations. These are functions. You can get an equation of what this graph would look like. Some of these are pretty complicated, and we'll get into what equations we can solve for these. But these graphs are what these slope fields create with this differential equation. Right? So f of x is a function, is a graph. We have some starting position, right, passing through the point 0, 0, like f of 0 when we plug in, right? This is like our x, right? This is x, and this is like y, right? So it's like the x, y here. Same things. It's just they write it sometimes like this, they write it sometimes like this. It means the same thing. It means that you have an initial condition of the graph passing through a certain point. Here we're passing through 0, 0. Here we're passing through negative 1, negative 1. And the function takes on a certain shape depending on where it begins. So that's what this slope field creates. All right, everybody? So that's a slope field, and it comes from a differential equation. It comes from a differential equation describing slopes, describing various slopes. Sometimes it's a y prime, sometimes it's dy dx, but it means the same thing, describing a slope. So we're going to try some of these, and you're going to graph these slope fields on some classwork right now. You're going to plug in all the different numbers and try to graph what the slope field will look like for different differential equations. And then you can see maybe what the graphs might look like, right? See what the graphs might do as you go through this situation. So let's try that.